Welcome. Pay attention now. This is the red bag. In this video, we will open this bag and we will discover magic. Magic about language, about the machinery of the language. The language is the tool of creation. Mother Nature doing magical thing with language and creating everything around us. Just look at under your skin, in the cells, in the DNA, what can be done with language. Although we as a programmers don't yet discovered piece of the language. In this video we will uncover and together we will discover the piece of the language, the machinery of the language. We will learn from Mother Nature how to make universal generic algorithm for processing any kind of written text in any kind of form. So this is the language tree. The language tree, human languages, we see composed as a language tree. We need to understand and think in these terms that of course these three branches, but we need to think in these terms. It makes sub-trees, it makes sub-languages. You need to have language to start with to make sub-language. I'm Georgian. Here is the Kartvelian subtree, here is the Georgian, and in Georgian the heaven sounds like samotche, and it conveys meaning like 3, 4, 3. On a slide we see this language tree is branches, or it makes 3 sub-trees, 3 main sub-trees. And where's the fourth? The fourth is the roots. So what are the roots? The roots are the most abstract definitions. You need to have language, source language, in which you can create new words like this. You write new word. For example, this is abstract definition. I took this definition. I lived this definition almost 10 years. So this is my definition. And you write S. Then from new line you write several, one or more, name defining paragraphs. I'm underlying idea of paragraph, not sentence, but paragraph, because paragraph can have several sentences. For in this case we defined S as a B and dot, one sentence. Then we defined it as S and A dot. Here we see its left recursive definition, and we don't have machinery at this time in computing to process this kind of languages with guaranteed deceiveness. So today we will demonstrate the minimum algorithm, how it's called, MVP, minimal valuable product, minimal valuable algorithm, how to do processing such kind of grammars, how to apply context in correct way. So here is the although we will discover it from information available to us. So follow. In the last sentence we see a left recursive name defined paragraph, but it has two sentences. Lately I add this second sentence in the last paragraph. So this is the roots of the language, how to make new words, in this case S. So why do we need this? Here is the definition of the C language. C is the one of the powerful languages we have in computing, because it can be compiler for C we have for every architecture. It means that C is translated directly to any kind of machine language. Although we can't say that C is the so-called least common denominator in languages, because C will compile it down to machine language. It will evaporate it. So in this video we need to underline this fact. We will understand how to grow languages, how to make sub-languages. So let's go there. So to make sub-languages we need CPU. This is the surface of the central processing unit, and think of it like a book, a dictionary which has written in the source language, for example, how addition is made. It's written in source language, and in this case, in case of our universe, of course, source language is the language of the circuits and language of transistors. So it's printed down with transistors. Here are some areas on the CPU. I'm just made arbitrary areas just to illustrate the idea that there are some groupings. Then we enumerate these groupings. We can think like we took a book and write there some paragraphs, and then we enumerated this book as a chapter. So we get numbers, actionable numbers. So to complete our sub-language, defining our sub-language, we need one more most abstract action. That action is fetch, decode, execute, loop. The responsibility of this action is to know how to connect everything together. So in human language terms, it is like let's take this book and interpret numbers written as a sentence with this book. This is the fetch, decode, execute loop in the human languages. That I'm underlying fact that we need to take some concrete book. In this case, CPU is a book. So how it works? It works like in CPU, in a computer we have a living paper like random access memory. So in memory we can write program like we see in the slide, and the program is written using text members. Here are now pay attention now. This is really powerful abstraction, text member. We need to underline fact that text member is an abstraction. All written languages are composed as a text members. Sentences of any kind of written language are text members, including languages, symbolic languages. Text members are grouped, some of them left to right, others from top to bottom, and text members are filled within with letters or numbers or symbols, but abstraction as a text member is really powerful abstraction, so we need to underline this fact. Now, we see several text members. They are in the red squares, and within those text members we see that there are various variable lengths, invariable lengths. So first text member includes 2 cells, second also, and third 4, and fourth 3. So how execution is going? The fetch, decode, execute loop has context. Think about context like as a humans we can process language naturally, like inherently knowing how to process language, and think about context like our eyes are focused on some concrete word always in the sentence. So the context, think about it like focus. So it has focus, and when fetch, decode, execute loop will turn, it will move focus to the next text member. It will decode the number within, in this case 0. It will redirect the current in that grouping, so it will turn pages and will start reading those groupings, and after it will finish every instruction in this CPU, at some point in time will redirect current back to fetch, execute loop. So it goes like this. Now it's time to 1, now it's time for 4, and so on. So here is the CPU, and here is the instruction set. Those are just numbers and some grammar how to compose text members using these numbers. In other words, how to compose sentences for to write in computer memory. Now we can summarize all our technology. Now we saw how CPU works. CPU is the generic Turing machine. It's a machine which Alan Turing made to parse and decode encrypted text of Enigma. And with all our today's technology, there are machines in mathematics, push-down automata, state machines to parse languages, to use power of the language. We don't have yet generic algorithm which can be able to process languages with guaranteed decisiveness. Today we will show that algorithm. So we have several algorithms. Some of them require to modify roots, in other words, the grammar of the language. They are all limited, you know. There is always shortest path from A to B. There must be shortest path. We don't need many algorithms. We need shortest one. So let us demonstrate, let us go there, let us learn from Mother Nature how to go there. So if we turn this arrow from A to B, shortest path look like this. So we are looking in the sentence like as a text members align in line, right? This is Georgian alphabet. It's 5th century BC, if I don't mistake it. And in the middle we see this beautiful cross. And I just want to underline similarities and about discovering and looking for language pit. We can look anywhere in the piece of tree, in the cutting of tree, and we can look text members can be as beautiful as we can imagine, right? So we can look. This is me sitting in my mother's kitchen within my father's house and looking in this mandala. So I'm looking in the sentence. We can imagine we are looking into the text members of sentence. We can imagine we see 3 text members of sentence, and the ideas of this is called time wheel, and we see the different colors and all of those details within, right? And I took inspiration from this and made this kind of protocol. The name of this protocol is Aradani, and Aradani name comes from Georgian word, Georgian phrase, and it sounds like this: Aradani Archevani, and it means not and or is a choice. And yes, it is. Not and or is a choice. Not and or is, these three junctions are the main junctions within logic, within node of mathematics, and all you need not and or to make any logical expression. So in this case, on the slide, we see text members aligned horizontally and vertically too. We can imagine the walking into text members as we saw in the slide, from the slide of CPU. We can turn walk. We can have another parameter in the context to turn work around and walk different ways in the text members. And with this protocol, we can imagine more complex and more expressiveness we can compose within sentence. For example, in the Georgian word, in the Georgian language, in the Georgian sentence, the sentence can be divided in the main 4 parts, and those parts can be composed with several text members. For example, subject or object within sentence can be composed with several text members, and in addition, they can be placed in the sentence in any order. So with this protocol, we can have junctions like we can see on the previous slide, not and or junctions, and how they work. We can follow these lines. Everything starts with yellow. And in addition, we can think why we need this in terms of while we are moving in yellow, then we turn again, those are times when different parts of the sentence, text members, must do their things. For example, this is time, in this fuchsia, time for subject to do its things. And then known, Shemas Menel in Georgian, and so on. In this way, the text members within sentence can be in any order, but they will be executed in the correct order anyway. So this is protocol of Aradani. I experimented with this protocol to try to solve the problem of deceiveness, to guarantee deceiveness, to solve halting problem at scale. At scale means at the level of the word. We are using these terms. We can group source language, in this case language of our CPU, our Turing machine, to have more powerful unit of composition, actionable numbers and actionable words. And within this with actionable word and with actionable syntax, we can solve problem of halting problem. And I tried different ways to lay out in the memory of the computer those text members dynamically to solve problem of halting problem. In essence, problem of left recursion is the halting problem. So in this context, in the context of language and actionable text. So it doesn't work in this way. It must be some other machinery. And the machinery is we need time machine. We need to enhance the central processing unit with the ability to move in interpretation time. So we can do this. And how we can do this? We can do this in a way. We need to imagine that Turing machine has the so-called tape, right? Let's imagine we have paper, 2D paper. Let's enhance Turing machine. Let's map 2D paper on the tape. We can do it. We can add alignments to each line to have 2D text. Then let's imagine we have two structures. This is I discovered it in the YouTube video, thanks to him who made this video available to me. And this is essentially, we see here at the left, quad tree structure. And we can make this structure as available as a walk for CPU, like text members composed in the connections like this. It's like making some more sophisticated structure to hold information, and we need two of these to apply context on this 2D paper, which can be static, like on the 2D plane. And all movements on this paper we will save within these two pyramidal-like structures. Every step in these quad tree structures can be imagined as a capstone. So we can build many different alternatives from here. And now, how this algorithm works. So we can imagine that our 2D text is like this. Every empty text member is filled, and it has same width each line, so we can map this on 1D array. And we have special syntax in addition, that we have first column, and in first column we only see 3, 1, 3, 1 and 0. This 3 means this is the starting of the definition of the name here, for example. After this follows name defining paragraphs, as we see here. And paragraphs are starting with 1. And the words which can halt execution are denoted as 2. And the words which never halt, which don't halt, is denoted as 3. So we need to solve the halting problem within these kind of definitions. And to understand this is the most abstract definition we can make for anything, for a name. So we need to imagine ways how to use this kind of this is new paradigm in computing. We need to discover it yet fully. So let us focus on an algorithm right now. The discovery, which is how to solve problem of left recursion, is within this simple idea. The sentence has two interpretation time. When we are at the beginning of the sentence, this is interpretation time when we are in front, and 4 means dot. And when we are at the end of the sentence, that means the interpretation time is different. We are at the end of the sentence. We already know something about S. This is S. We place dot, so we know S. So after this, we can continue any name-defined paragraph for S, which is left recursive inside, and it works within indirect left recursion too. So let us show the demonstration of the algorithm. So idea is that we use these two pyramidal-like quadri structures to build execution plans. While we are moving down in the word, for example, while we are trying to interpret some symbol which may have several name-defining paragraphs, we are saving on the alpha pyramid. That's the pyramid we use to come back to original sentence. How to come back? Then we are saving the where this name-defining paragraph starts for this concrete symbol. And last one, we are making top for CLR. CLR meaning check for left recursion. Top means that this is the top. This is the symbol after which there may be left recursive definition. I.e., we need this to solve halving problem. So we always are in some word. So now we have here the first sentence, and this is 3, means that after this comes name-defining sentence, name-defining paragraph. And here we are in the name-defining paragraph. In name-defining paragraphs, we have several books, like we saw in the CPU slide. CPU is a book with which fetch, decode, execute loop. So in this machine, we created several of those kind of books, and those books are interpreting numbers differently. With Blue Book, we always start with the first, we are always at the starting of interpretation time of the sentence. So with Blue Book, we go into the first text member, which is 1. It must be 1 or 3. In this case, it's 1. Then we save on the second pyramid, on the yellow part, what we need, how to continue. We need to continue with Blue Book, next name defining paragraph. But before we do this, we need to go right side. So we saved here cursor in time to go back here. Let us diverge. In computing, we have algorithm named backtracking. We don't need backtracking. We need time machine. This is algorithm which works and saves exact point in time. So when we come back, we restore everything we know exactly to this point. So we are moving right now. We will forget everything about moving right when we continue here. So right now we are moving right in interpretation time. So we changed book. Note, we changed book. This is yellow book. Now we are with yellow book in 3. And first we will check left recursion. If we see that we are recursing left recursive, it is left recursive definition, we will skip. We will skip and we will continue with cursor. We will continue next, trying next name defining paragraph. If it not left recursive, or if we decidedly say that this will not halt, then we mark name defining starting position for this symbol. We will find this symbol in the to space text. We will save that position like we have here, and we will save on the pyramid. Pyramid has 4 sides, and each color demonstrates those sides. And we will save another side, like in quad tree structure we have 4 rays, right? Those 4 sides. So we're saving how to return back, and we are going into first name defining paragraph for this symbol. In other words, we are here for another symbol, right? And we know this is not left recursive because we checked. We made check. At some point we will return, and how we will return we will see. Just we need to go to that. At some point we will encounter dot and we will go back. So let's go right now. Let's go right. So at the right, while we return here, we change the book because there is no way we will halt because we already skipped that point with yellow book. We already knew some base case. There are dot encountered below us, right? So we changed book of interpretation. We are right now with green book. With green book, we just interpret 2 as a we need to interpret it, and then we go next. And in next, we are also within text member, which holds 3, and this means as an immediate value it holds some symbol. We need to interpret those name defining, find those name defining paragraph and interpret each one. Place each one at this interpretation time. So right now we are doing a little bit different. We don't check left recursion chain because we need to make new one. We are top in this case for left recursive chain. This symbol will be top. Then we'll do same. We will save the name defining position where name defining paragraph starting, and also how to come back. We will do same. And where we'll come back, we will encounter dot. And where we will encounter dot, we will make another CLR, check for left recursion, but it is different now, little bit different. Let us discuss in just a moment, but it is different with more longer strides, like. And we will save here 2 cursors. First cursor to try another sentence after this sentence when we finish interpreting current combination, and another cursor to try all those name defining paragraph which we can know where they are starting from this information, from this maroon, and we will go back in the parent sentence. And in the parent sentence, we will go back and go right in this way. We are investigating here and discovering here. At some point in time, we will reach to end, and will activate cursor. And cursor will activate it is red because we placed this last. So this red cursor will be activated, and now it's time to the yellow activate red cursor, and now it's time to go in and try all name defining paragraphs, but this time with red book. So we go into with red book, we interpreted with red book number 1, and it means we need to save again cursor to continue interpreting next name defining paragraph. We placed in interpretation time. In interpretation time, we are after dot right now because we are in red color. We are using red book, and we are going with to write with purple book. So with purple book, if we see 2, this means it can be left recursive definition. So we will go to yellow cursor and try next name defining paragraph with red book. If it's 3, we will check chain, CLR chain, and in CLR chain, if it is left recursive, we will skip this diving process to finding all definitions for this, and we will go straight to continue with the right part of this sentence to add here all the definitions. But if it not left recursive, then we will make information of the time pyramid on opposite time pyramid, how to return back, to this part, and we will dive again into definitions to find definition for this symbol. But in this time with Redbook. And with Redbook we will continue this chain. And this chain will match to correctly, meaning we will correctly handle all indirect cases of the left recursion. So after we finally found their left recursive definition, we will return here. If we don't find the left recursive definition, this means that this sentence will continue with green, and if it does not have green, we will try another, which means we will continue here, right? So this is how algorithm works. And another case, while we're working with red down in the name defining paragraphs, we may encounter another starting point for other symbol. This is denoted as 3, or at the to the end of the paper. And in this case, if we are in red, we just take another cursor. Or it may be that we are working with blue and we encounter and we will interpret the same in the same way. With blue also we will interpret this as to go back to yellow cursor. So on a slide now we see this algorithm, all it takes. It's implemented purely in C. In other words, actually we can say this is the machine language. It will work at the speed of the machine language. And we are here using colors extensively. So here are our fetch, decode, execute loops for little CPUs, if you will, little sub-languages for each book. And how all those are composed we see here. We are using macros to access and build CIDs of this quad tree. We have colors to denote the opposite sides of this tree. So we can see everything has two sides, right, in the universe, men and women and black and white and so on. So we need those two structures to dance within, to go down within interpretation in the deep of the definitions and go back. So colors like maroon, olive, lime and navy are for one side, and yellow, green, red and blue are for other sides. So this is how this algorithm looks like in the code, how it's coded. So another way to think how this idea solves this problem of deceiveness, how it guarantees deceiveness. It guarantees deceiveness. We can explain it in more human words, like we all can be considered as machines, like electric machines, right? So we all have a choice to make same thing in a cycle, and we can cycle within doing same thing and doing same thing. But how our halting problem is decided. We will halt anyway. We will given time, right? So we can do something all time, right? We will halt, right? Sooner or later. That's how same thing is translated in our sub world. When we created this sub world within its own language and made those structures where we saving time, it means we converted space into time. It means we have space-time manifold, right? So we converted space into time. So within this algorithm, we can identify places to check usage of our time. Do we have time left or memory left in this case, because we converted space into time? If we have, we can continue. If we don't have, we can gracefully halt and say, hey creator, I am halted. Here is my exact state. Take it. If you want, you can run me on a bigger box. That's how it's done. So let me demonstrate the algorithm in more dynamic way. So here we see how the text is written on the array. Here is the macros we are using. This is just an array, how the text is written as in numbers. Each text member are in 11 cells wide. In the middle we are placing actionable number, and we have some immediate values like we are placing here, for example, name of the symbol, and in the first row we are placing same symbol to identify that from this line all those name defining paragraphs are for this symbol, right? And we are aligning it with this macro to align, and how it looks like. It looks like this. We made debugger. When you are in language processing, making debugger, making this kind of thing is, imagine we are making little CPUs. So after we make some progress or make some really valuable thing, we can transfer it directly into hardware. So that's how it's can be transferred into hardware. So here is our debugger. This is debugger, and here is our color. So we are looking at this structure, at this quad tree structure or pyramidal structure from the bottom. We are looking for first pyramid, yellow, red, blue and green, and we can turn, and now we are looking at the second, or we can turn full duplex mode. We are looking at the same time both of them. So right now we are on the member on the first sentence, and we see number 3, and we are here with the yellow book. So we see number 3. We are here with the green book, and green book means we are on the first sentence. It means that we are not in the some kind of symbol already. We are interpreting the first sentence. So we will make here CLR top, and we will go with the book of Navi. It means searching book. We will start searching. We will find the correct symbol. Then we, with blue book, will try to go right side. With blue book we will go down, and with yellow book we will go right side. We will see 2. Then we will continue with green book, and so on. Here we are at 4, right? We will save the interpretation time. 2 cursors. Here we see we added 2 cursors, 2 and 3, and we will take road to finish current interpretation. So we finished it. We printed it on the console. Here is B. Then we use the cursor to continue. Now we are continuing with red, meaning we are here at interpretation time. Now with red book, we will skip this because this can be left recursive because this is number 2, right? So now we are number 3 and it is indeed left recursive definition. So we will skip, we will don't go down searching this symbol, we will just add A here. And now we are in the second dot. In this case, in the interpretation time here. Now we, with the green book also. Now we'll do same. You can see here how we adding, how we interpreting strings. And like this, we can go and make we can dance like this. It will, right now this algorithm will not halt gracefully because this algorithm is attached with debugger. I will show repository. Here we see two versions, sophisticated C and sophisticated 2. This version uses stack to build quadris, and the second version, it's a standalone. It doesn't use stack, it don't use anything at all. It uses pure memory array, when with this algorithm is more sophisticated in terms of it will guarantee decisiveness. Here we are checking space. So we can run this. For example, we can see that in the main we are running expression grammar, and the expression grammar is this ambiguous grammar. But as we can see, it's not a problem for this algorithm because it guarantees decisiveness, and when it will halt, I'm saying just continue with another cursor. So we can see all mathematical expressions with the space we are giving him. Right now it's 3000. Let's try a little bit bigger space. So we see all those are mathematical expressions, right? So, and they are not in correct order. We are seeing them from right to left. So that's why those are in not correct order. But all those are mathematical expressions. And this algorithm will work for any kind of grammar and will guarantee decisiveness. So any kind of feedback, I will appreciate any kind of feedback, and I really want to express that there are several years, 2 or 3 years, I promise that I will solve this problem. So many I became in the captured with my own words. So for me now it's the time when I trying to give all this what I have. So any kind of feedback I will appreciate, and thank you very much for your time, and bye.